All right, guys, and we're doing just a couple quick sections out of Chapter 9 here. This is a topic that we do need to cover for the AP test, and it was something that they've added to the curriculum some time between when I was in high school and then when I started teaching AP Calc, and that's the concept of differential equations. This is kind of a separate branch of calculus that ties in pretty well with what we're doing here with integral calculus in the second semester. And for those of you who are thinking about doing engineering or something else really technical in college, it is very likely that once you guys complete the sequence of Calc 1, Calc 2, and Calc 3, you might very well have to take a separate course just called differential equations. But all we're doing here in 9.1 and then a little in 9.3 is giving just a little bit of an introduction to what differential equations are and how to handle them. So a differential equation, first of all the cool kids are going to abbreviate that as a diffie-Q. All right, I don't want you to get laughed at when you go to college and call it by its full name. A differential equation is simply an equation, thank you, Captain Obvious, in which a derivative or a differential is given to you rather than the function itself. So a differential equation is usually going to look something like this. Instead of giving you an explicit definition for y, they're telling you what y prime is, or dy dx, another way of putting it that way as well. So the function being given to you is the derivative of some other function. And what we're attempting to do here in a differential equation problem is find a solution to a differential equation. So essentially, they're giving you a derivative, and they're telling you, find the function that has this as its derivative. And you may have already figured out in your mind what it is that we're going to be doing here. If you know the derivative and you want to find the function that has that as its derivative, we are going to be anti-differentiating. So this really isn't a whole lot different than what we've been doing for the last couple of months. It just looks slightly different here, and we're doing it in a different context, but the skill itself is pretty much the same. So again, they're going to give you y prime or dy dx, and they're going to ask you to solve that differential equation by coming up with the value of y. And then notice the notation as well. If what they gave you was little f of x, we're trying to come up with capital F of x. And as we talked about back when we were doing what? Fundamental Theorem of Calc Part 1, I want to say, back in section 5.4, if I'm not mistaken, that capital F of x is used to denote an antiderivative of little f of x. And with the plus c at the end, and hopefully you remember where that comes from, that is going to give us something we're going to call a general solution to a differential equation. So there's two big styles of problems I wanted to work on. But before I get to those two, I wanted to start with this type of problem right here, simply because, if I'm not mistaken, this is what your homework from section 9.1 in the book is going to start off with. And in years when I've not gone over this, people rightfully get really confused and say, wait a minute, what's going on here? And I don't want you guys to panic right off the bat. Now, this word right here, verify, students either usually ignore that and don't think anything of it, or if they do think about it, they get a little bit scared. Verify means prove that something is true. And I just said the dreaded P word in math, prove. But with verification, it's sometimes a little bit easier than that. They have given us, right here, everybody, a differential equation. And what makes it a differential equation is the presence of this y, no, not that, is the presence of this y prime located right here. So that is y times the derivative of y plus 4x is equal to 0. That's a differential equation because it contains a derivative. But what they've also done, and boy, this was nice of them, they gave you the solution to this differential equation. They've said that the solution to this mess is y equals 12 minus 4x squared to the 1/2 power. We just have to verify that this y value right here, or this function, is in fact a solution to this differential equation. So verifying is kind of a nice way to ease into these problems here, because they've given you the answer. They just want us to show that it's true. Now, what we're going to be doing is using this idea right here, that y is equal to that mess right there, but we're also going to need to find the derivative of y, which is dy dx, or I'm just going to call it y prime here. So right underneath that, let's go ahead and differentiate what they gave us. We're going to have a 1/2. The 12 minus 4x squared is going to get taken to the negative 1/2 power. So thinking ahead, the 1/2 is going to give me a 2 on the bottom. the 12 minus 4x squared is going to get taken to the negative 1/2 power, which is a square root in the denominator of the same radicand, 12 minus 4x squared, and then we're going to multiply that by the derivative within, which is going to be a negative 8x. That's going to go up here on the top. And I guess I can clean that up just a little bit here by dividing out that 2. To say now that y prime is going to equal a negative 4x divided by the square root of 12 minus 4x squared. So I had a box around y, and now I'm going to box up y prime. And now that I know y and y prime, I am going to take those two expressions and substitute them in for y and then in for y prime in the original differential equation that they gave us. So let me switch colors here. I think I'm going to go to blue on this one. And here we go. So I'm really just recopying this original equation, but with substitution. The y becomes, I'm going to go ahead and make that a square root rather than a 1/2 power. But the y is the square root of 12 minus a 4x squared. And that takes the place of our y. Multiply that now by y prime, which is a negative 4x over the square root of 12 minus 4x squared. So there's y times y prime plus a 4x should equal 0. And again, the directions are to verify that. I just need to make sure that I can simplify my left side and get it to equal exactly what the right side equals. And I don't think this one's too bad. We are multiplying by the square root of 12 minus 4x squared and then dividing by that. So they simply cancel each other out. And we're left with a negative 4x plus a 4x should equal 0. And last I checked, those two terms are opposites, so when we add them, we're going to get 0 equals 0. And when you've got your left side and your right side equal to each other, you have verified the original statement or the original identity, and hooray, we got that one right. So, without a little push in the right direction, people usually don't quite know what to do on a problem like that. That's how we figured it out, guys. We needed to know the values of y and y prime, both in terms of x. They gave us y. We figured out y prime. We plugged them in there, and we got a true statement. Let's do one more of those just to make sure that we've got it. Little more complicated diffie-q now. This x squared minus 1 times y prime plus the product of x times y should equal 0. So let me go back to purple right here. Again, just like the last problem, they gave us the solution, everybody. They told us what y was. We are now going to need to come up with the derivative of that y prime. So let's see here, everybody. That is going to be, and you know what? We're going to have a negative 3/2 power right here. So I'm not going to write this one with radical. I'm going to leave it with a fractional exponent here. Y prime is going to equal a negative 2. And actually, I'm thinking ahead here, guys. The 4 times the negative 1/2 is a negative 2, but eventually we're going to have to multiply that by the derivative within, which is going to be a 2x. So the negative 2 times the 2x is going to be a negative 4x, multiplied by the same base of x squared minus 1, and that's all going to get taken to the negative 3/2 power. And normally right now I would worry about the chain rule times the derivative within, but I already did that. That 2x from the derivative within got multiplied by the negative 2 to get me the negative 4x out in front. So that, everybody, I believe, is our derivative. And now that we know all that, let's go to the original equation right here, and let's see what we can do to clean this up a little bit. Now, if you haven't noticed, and I think I said this in passing before, our goal here really is to try to replace all of the y's and the y primes and get everything here in terms of x. So that is going to leave us with, nope, not that, the x, oh, for crying out loud, the x, oh, something weird is happening here, ladies and gentlemen. Hang on a second. You do that, and do that, and do that, and do that. Let me undo all of this gibberish. Okay. Maybe. Oh, wow. I undid everything. That was not good. We want to do this and this and this and this. Okay. Gotcha. So let's try this one more time and see if this works. X squared minus 1. Gotcha. Multiplied by y prime, which is going to be a negative 4x, multiplied by I don't love the way I did that. I'll keep the negative 4x in its own set of parentheses, multiplied by x squared minus 1 to the negative 3/2 power. So that is the first term here, plus x times y. So the x multiplied by this y right here is going to get us a 4x times x squared minus 1 to the negative 1/2 power. So that takes care of the x times the y, and all of that should be able to be whittled down to just get 0 here on the left-hand side. Now, how can we do that? The one thing I want you to notice right here is that in the first term on the left, we've got an x squared minus 1 multiplied by the same base to the negative 3/2 power. Well, let's remember that that is an exponent of 1 right there. And when you are multiplying two monomials with the same base, you keep the base the same. I'm going to bring the negative 4x out in front. You keep the base the same, so that'll be x squared minus 1, and we add the exponents together. A positive 1 and a negative 3/2 is going to be a negative 1/2 power now for that exponent. Oh, and this is much more convenient than I thought it was going to be. Plus, I'm not going to do anything to the second term, 4x times x squared minus 1 to the negative 1/2 power should equal 0. Well, what I just noticed, and I hope that you guys did too, these two terms are like terms. They both have an x. They both are multiplied by x squared minus 1 to the negative 1/2 power. So we would simply add their coefficients in order to combine them. But not only are these two terms like terms, they're opposites of one another. They're exactly the same, other than the fact that the first term is negative and the second term is positive. So anytime you add two opposites together, guess what? They wipe each other out, and we get 0 equals 0. And there you go, guys. We have verified that differential equation and its solution as well. Okay, not too bad. Now, as fun as those two problems were, this problem right here, I want you guys to put a star by this section, actually. This, and the next, we've got 4 more examples to do together. This is much more in keeping with what you're actually going to be asked to do on quizzes or tests or on the AP test as well. I should tell you this right here. These types of problems that we just got done with, they show up on your homework, but they really don't show up on the AP test or any of the prep materials for that as well. But this is something you are going to see. Find a general solution to each differential equation. And if that phrase sounds familiar, let me take you back to the first slide right here. When they give you a derivative, y prime equals some function, if we can solve for y is equal to capital F of x plus c, that's what we call a general solution to a differential equation. So they've given us y prime. We're supposed to figure out what y is, but no, there should be a plus c at the end of all that. Now, what I'm about to do for you just once, I won't do it very often, guys, is to rewrite that y prime in a more formal way of dy dx is equal to an x squared plus an 8x and a minus 3. And now, I'm going to show you guys just something a little bit weird right here that you don't really need to do on this problem, but you will need it to do on future problems. The dy dx on the left-hand side, we tend to think of that as one singular entity. Dy dx is one thing, and it's really not. It really is just a fraction. Dy divided by dx. And if I were to multiply both sides of this equation now by dx, this might look a little bit familiar to something you guys had seen back when we did u substitution. The dx's on the left are going to cancel each other out, and we're going to get dy equals, and now we have an x squared plus an 8x minus 3, and technically all of that as a quantity is getting multiplied by dx. Now, you don't really need to put the parentheses there, but it's certainly not a bad idea. And what we have now on the left, everybody, is dy, or the derivative of y. And as we're looking for a general solution to a differential equation, we want to know what y is. Not dy, but y itself. So, how do we go from the derivative of y back to y itself? We are going to anti-differentiate the left side, and of course, if we're going to do that, we also need to anti-differentiate the right side. And what I'm hoping you guys notice there, I know that the variable of integration is not something that has interested you guys at all, but you really can't have an integral without a dx or a dy at the end. So we've got an integral of dy on the left, and on the right, an integral of x squared plus 8x minus 3, but taken with respect to x. If we hadn't moved the dy dx, let me just show you real quick what this would have looked like. Don't change this in your notes. If we hadn't done what we did earlier, this is where we'd be standing right now. And I know you guys don't think much of it, as I said, but that's an incomplete integral right there because there's no variable of integration that comes after the integrand. And technically, that's bad. All right, so that's where we're at right now. People tend to understand the right side of this equation better than they do the left. And let me just remind you, it looks like an integrand is missing on the left-hand side. We'll just go ahead and cram a 1 in there if you need to see it, guys. The integral of 1 dy, and we'll work it that way. Now, I do want to point something out right there. I just kind of applied the fundamental rule of algebra to this equation. Do whatever you want to the left side, as long as you do the same thing to the right. And we're integrating or anti-differentiating on both sides. But one thing I do need to point out is that we don't need to anti-differentiate with respect to the same variable on both sides. On the left, we're anti-differentiating or integrating with respect to y, and on the right, we're doing it with respect to x, and that's okay. We'll verify that at the end here. Okay, guys, antiderivative of 1 taken with respect to y. This is why it's important to know what variable you're dealing with right here. That just becomes a y. Are you sure about that? Well, let's double check it. The derivative of y is 1. So yeah, I think we're in good shape right there. And on the right side, this is a little bit more like what you guys expect to see. Antiderivative of x squared is going to be a 1/3 x cubed. Antiderivative of 8x is going to be a plus 4x squared. And the minus 3 is going to turn into a minus 3x. Because this was an indefinite integral, we're going to put a plus c at the end. And everybody, we have solved for y now, and we have it expressed solely in terms of x, so that is the general solution now to this differential equation. And if you're not sure if your answer is right, or if you want to be extra careful here and make sure you've got it, take the derivative of that. dy dx is equal to, well, this is going to sound familiar. 3 times 1/3 is 1 times x squared plus an 8x minus 3. Whatever that constant is, its derivative is going to be 0. So that is the derivative of our answer, and that is exactly what the original differential equation given to us was. They used a y prime and I used a dy dx, but that means the same thing. So this step right down here on the bottom in green is not necessary, but it's just a way to verify the answer that we came up with. So I sometimes don't make this clear enough year in and year out. The answer to this problem is what I have in the purple box right here, guys. We were looking for the function that we can call y represented solely in terms of x. So essentially, you're just integrating the left and you're integrating the right, and then boom, that'll pretty much take you directly to the answer. These steps in the middle right here are just formalizing and confirming some of the things that really we need to have from a technical standpoint to get that right. But practically speaking, a problem like this is going to be pretty quick and easy for you. Now, example B is going to be a little bit tougher, guys, and so I made myself a little note right here to have for you guys in there as well. This example really illustrates a concept that I kind of hinted at in the last problem, and it's called separation of variables. You go ahead and write this in your notes, everybody, and put a big box around it. And the main idea to take from this, a differential equation cannot be solved, at least not with any of the methods that we're going to learn this year, unless you first completely separate your variables. And what that means is all of the y's, including the dy, need to be on one side, usually the left, and all of the x's, including the dx, need to be on the right, or the other side, I should say, and that's normally the right. So that's really our first step with any one of these problems, is if you've got an expression or an equation now that has x's and y's together on one side, you need to make sure that you get them split up. So the first thing we're going to do here, and as I said, it almost always works out that we want y's on the left and x's on the right. So the first thing I'm going to do is add this x over here onto the other side. You don't really need to show this step, but just because it's our first one, I thought I'd write this out. And at the same time, because it really does help us. I'm going to rewrite the y prime in its more formal way of dy over dx. So that's y times y prime equals, and adding the x to the other side, we just get an x over there. Now, we've made progress, but we still have one thing on the left that needs to be moved. To separate the variables, the dx on the bottom of that derivative fraction needs to be moved to the right. So we will do that by multiplying both sides by dx, and those two terms, or I should say factors really, are going to cancel themselves out. And we're going to get y dy is equal to, and an x dx. Now, we've completely separated our variables. The left side contains only y's, the right side contains only x's. And now that we've done that, now we are ready to anti-differentiate both sides of this equation, even though we're doing it with respect to different variables. And now you'll notice we're basically playing the same game here twice. The antiderivative of y, taken with respect to y, is going to be a 1/2 y squared. Now, technically, don't write this down. Technically, there's a plus c that comes at the end of that. All right, equals, and now it's really the same story on the right. The integral of x, taken with respect to x, is going to be a 1/2 x squared, and technically there's a plus c here as well. Now, I got to warn you what some people do. What some people want to do here is say, well, I'm just going to subtract a c here and subtract a c here, and that's gone, and that's gone, and therefore there is no c, or there is no constant in this equation. The problem with that line of thinking, everybody, is that we're treating c like a variable, and it's really not. If you remember what the c means, c can represent any constant in the world, of which there are infinitely many. And so to do what I just did right there with canceling them out is to assume that the two constants, the one on the left with y and the one on the right with x, is to assume that those two constants are the same. And the chances of those being the same are next to nil. So what we really should have done, what would have been a little bit more formal here, and again, you still don't really need to write this down, guys, yet. If I called that C1, and this one's C2, then, okay, I'll subtract a C1 from both sides. But what we need to realize here is that while these C1s will cancel, the two on the right don't. A constant 2 minus a constant 1, when we combine them, is just going to make another arbitrary constant. And just like C1 and C2 themselves, we have no way of knowing what that constant is. So for all that reason, everybody, what really happens when we're doing a differential equation like this is when we're doing an antiderivative of the left side here with y, we don't put the plus c right here. What we do instead is simply, this is just kind of a habit right here, we simply just put the plus c once over here on the right-hand side with the x. All right, so that's the reason why we don't include the plus c right here, even though technically there would be one. We would just immediately bring it over to the right, combine it with the other constant, and get some other value c there. So here's where we're at right now, guys. 1/2 y squared is equal to 1/2 x squared plus c. And our goal, I got to remind you guys of this a lot as we're getting started, our goal in solving a differential equation is to get y by itself. Get y strictly as a function of x. So that is always the goal here after we anti-differentiate. Let's get y by itself. How are we going to do that? First thing, we're going to multiply both sides by 2. And right away now, I got to show you guys something funny. I'm going to multiply the left side by 2 and the right side by 2, and sure enough, the left side is just what you'd expect. The 2 and the 1/2 cancel, and we end up with a y squared equals. And on the right side, we see a constant, 2 times a binomial, and our inclination is to distribute that 2, which we are. The 2 times the 1/2 x squared is just going to be an x squared, but again now, what most people want to do is put a plus 2c here. That's what we would do if c were a variable, but it's not. C is an idea. C is a concept. C is a placeholder. C represents some constant. And so the way we need to think about this is when I multiply 2 times an arbitrary constant, what do I get? And the answer to that is a constant. We don't know what that constant is. We're not declaring a value for c right here, but 2 times a constant is just a constant. So we just label that as c. All right, that's a little bit weird there, everybody. That takes some getting used to. This whole concept of dealing with c, the constant, is fuzzy math, and it's something we're going to have to get used to. Almost done, though, guys. To get rid of the square on the y, we're going to take the square root on the right and the square root on the left. And I have to remind everybody that you do not take a square root term by term. So what I've just done here is incorrect. I see a lot of people now tell me that y is equal to x plus, and even if they get what I was saying before, that the square root of a constant is a constant, this is not the right answer, what I have drawn right here, okay? What we need to do is take the square root of the entire right side of the equation, and there's no property, guys, that says that we can simplify the square root of a sum or a difference. So this is going to be y equals. Now, technically, there's a plus or minus there in front of that radical, and this is simply the square root of x squared plus c. And that, everybody, is as much as we can do to clean this up. And that is our solution here to this differential equation. All right. So, fun stuff. The last 2 problems I have to do with you really aren't much different than the 2 that we just did, except now we're working on something called an initial value problem. And I even wrote down here for you guys, and I think it'd be a good idea for you guys to put this in your notes too, an initial value problem. That's what I meant by, well, let's see right there, initial value problem, or an IVP. It is simply a differential equation, but an initial condition is given to you, which allows us to solve for c in order to find something, not a general solution, but rather a specific solution. If we look back at the last 2 problems that we just did, the presence of that plus c at the end of this solution means that there's actually an infinite number of functions out there that satisfy this original differential equation. They all look like this, but they can have any value they want in there for c. So for example, the square root of x squared plus 5, that would work. The opposite of the square root of x squared minus 9, that would work. And I could sit here all day and keep coming up with them. Likewise, this one here too. Okay, 1/3 x cubed plus 4x squared minus 3x, and then whatever constant value I wanted to put at the end, all of those would work to satisfy the original differential equation. But once an initial condition has been given to us, there is only one specific solution out there, guys, that does what we need it to do. So let's take a look at example A. Y prime is equal to cosecant of x times cotangent of x, and they've also given us this initial condition. In fact, I'll write that down. That is your IC, your initial condition or your initial value, meaning that when x is equal to pi over 4 in the original function, our y value has to end up being 0. So let's see what this looks like. Okay, at first glance here, guys, I'm going to go a little quicker here. This one is already separated. All of the y's are on the left, all the x's are on the right. Technically, I would move the dx, but I think you guys probably get it. So I'm going to go ahead and integrate the left side and the right side. The integral of y prime is just going to be y. Ah, dang it, I did it again. All right, undo that, undo that. Let's try that again, Mr. Fontana. We just get y equals, here we go. And now, as I'm hoping you guys recall, negative cosecant of x, cotangent of x, is the derivative of cosecant of x. So this right side is going to become negative cosecant of x. All right, and a plus c at the end of all that. So what we have right here, everybody, is the general solution to this differential equation. Now it's time to use the initial condition to try to figure out the value of c. So what I tend to do here is I tend to switch colors and move this to green, and then I also tend to indent just a little bit. And what we now know is that if we look at this general solution, there's actually 3 variable quantities. There's y, there's x, and there's c. Our goal is to solve for c here with this initial condition. So to do that, we need to have values to put in for the y and the x. And that is where these values come in right here. As I said earlier, when x is pi over 4, y is equal to 0. So my y value becomes 0. Like I said, I like to indent just a little bit. And this is now 0 equals the opposite of the cosecant of our x value at the initial condition, which is pi over 4 and a plus c. Now we're down to just one unknown. So let's solve for that. 0 equals, and here we go, guys. Oh, I don't know. Let me see here. Cosecant is the reciprocal of sine. Sine of pi over 4 is root 2 over 2, which, if you remember from its non-rationalized form, is 1 over root 2. Cosecant is the reciprocal of that, so that is just the square root of 2, and I have the negative out in front of that. And we'll add the c at the end. And again, our goal here was just to solve for c. So I'm going to add that root 2 to both sides and get c equals positive square root of 2. Now, I don't know. I'm kind of reticent to box that or circle that. This is not my answer, but it's a start. Okay, so where are we going next? Give me a second here, guys. Let me do that and this. And I think we're in good shape. Now, back to it. The main important idea right here is that solving a differential equation isn't done until we've got y completely by itself. So what we're now going to do, guys, is go back to the general solution that we had right here, but now we are armed with the correct and known value of c. So we get y equals the opposite of, nope, not that. The opposite of the cosecant of x, and then a plus square root of 2 at the end. Now again, our goal here would be solve for y strictly in terms of x. Well, everybody, I think we've got it. And I think that is the solution to this initial value problem. So let's verify what's going on right here, guys. All right. What we have found, or at least what we think we have found, is the one and only function in the whole world that does these two things. It has this as its derivative. Think about that real quick. Derivative of cosecant of x is cosecant of x cotangent of x. So therefore, the derivative of negative cosecant of x would be positive cosecant of x cotangent of x. And the derivative of that constant would just be 0. So yeah, the function that we wrote, that we boxed, has this derivative. And now let me be clear, there's an infinite number of functions that do this, but only one of them also passes through the point pi over 4, comma 0. And to verify that, well, we really did this already, cosecant of pi over 4 is root 2. The opposite of that is negative root 2, and plus root 2 means that y would be 0 when x was equal to pi over 4. So there's an infinite number of functions that have this derivative. There's an infinite number of functions that pass through this point, but only one function does both of those things, and we found it right here. So there's no ambiguity. There's no uncertainty here. There's no plus c. There is one and only one function out there that has cosecant of x, cotangent of x as its derivative and contains the point pi over 4, comma 0, and we found it. So that is the one and only solution to this initial value problem. Hooray! Okay, and the last problem I want to do with you guys is actually a good bit harder than the one that we just did. This is actually an AP question, everybody, off of the, going way back now, the 2008 AP exam, problem number 5B. I'm not sure why I thought that was relevant, but in case anybody wants to look it up, there you go. So look at what they've given you here, guys. dy dx, that's a derivative, is equal to y minus 1 over x squared. So there's the derivative. And they've given us an initial condition here that f of 2 is equal to 0. So again, when x is 2, y is going to equal 0. And our job here is to solve this initial value problem and come up with the one and only one function that has dy dx here as its derivative and passes through the point 2, 0. So first thing we need to do, this one's more complicated than the one that we just did, we need to separate our variables. We want all of the y's and the dy on the left, all of the x's and the dx on the right. And so I don't mess this one up too much. I think you guys can kind of see what's happening. We're going to need to divide both sides of the equation by the y minus 1 that's in the numerator on the right. So my left side is going to become a 1 over y minus 1, and that's getting multiplied by dy equals. Now on the right side, I got rid of the y minus 1, but the x squared is still there, still where it was in the bottom of a fraction. So that right side is going to become a 1 over x squared, and I'm multiplying both sides by dx, so that gets me that. Now, guys, I mean, this is only what the second, or really the second problem you've seen where we had to separate our variables. So if that wasn't quite as easy for you as I made it look, that's okay. You guys do what you need to do in terms of multiplying both sides by this and dividing both sides by that and showing any steps, but hopefully that makes some sense to you guys there. Okay, that's where we're at right now. And now that we have separated the variables, we are going to anti-differentiate the left and the right. So here we go. And I'm hoping you guys remember this. On the left side, anytime we anti-differentiate a constant, like 1, divided by a linear function, like y minus 1, this is when we are now going to get the natural log of the absolute value of that linear function on the bottom, which in this case is y minus 1. Technically, divided by the derivative within. So real quick, guys, if this was a 5y right here, this would be a 5y here, and I would now need to divide by that 5 or put a 1/5 out in front, reversing the chain rule. But as it were, in this problem here, the derivative within is just 1, so I can get away with ignoring that. Also, I can get away with ignoring the plus c on the left side because I'll deal with that on the right. Now, if what I just said about the left side becoming natural log made sense to you guys, I've got to warn you that there are people out there who are going to now say that the right side is going to be the natural log of the absolute value of x squared. They think, well, we're doing the same thing on the right now that we did on the left. And that, I'm sorry to say, is incorrect. Let me go back and say again what I said a moment ago. When you are anti-differentiating a constant divided by a linear function like y minus 1, that's when your antiderivative is going to be natural log of the absolute value of the denominator. But that is not what's happening over here on the right. This is not a constant divided by a linear function. It's the 1 divided by x squared. So we got to do that one really, just thinking about the power rule, everybody. This, what we're anti-differentiating here, is x to the negative second power. So we'll keep the same base, which is x. Maybe we can do this in our head here. That's x to the negative second. Anti-differentiating that, we raise the power by 1. So our x to the negative second, that was ugly, when we anti-differentiate that becomes an x and we raise the power by 1 to get negative 1, there we go, and then divide by that new exponent. So that is going to be a negative 1 over x, and here is where we put the plus c. Okay, that's where we're at right now. We have anti-differentiated both sides, and there's two different schools of thought on what to do next. One way, and the way that I used to do these problems, is to keep manipulating this equation that I have here in purple to try to get y by itself first, and then come back and use the initial condition to solve for c. However, most of the AP practice material that you guys are going to get does it a different way. And I've kind of changed my mind on this over the years. At this point, now that we've anti-differentiated, I like to kind of take a pause and use this value here to try to find C right now. Then we'll come back to this equation where we left it right here, and then we'll solve for y. So I'm going to indent here. I'm going to switch to green and say, all right, the natural log of... And now, in this initial condition, my y value is 0. So that's the absolute value of 0 minus 1 equals the opposite of 1 over my x value there is 2 and a plus c. Okay, so we subbed the 2 in for x, the 0 in for y, and now let's see if we can't solve for c. Let me make a little mark down there, and that allows me to zoom and scroll a little bit better. Okay, I think that's what I need right here. So what's going on here, guys? The 0 minus 1 is negative 1, which is a problem because the natural log of negative 1 doesn't exist. But because of the absolute value, that becomes the natural log of positive 1, which is 0. And that equals a negative 1/2 plus c, so we get c equals 1/2. Now, I do want to warn you guys for just a second. If you're doing one of these problems and then you ask a friend to see their work, it is possible that they might have a different value for C than you have. That just depends on when during the process you guys decided to use the initial value and solve for C. However, with what we're about to do next, we should all get to the same spot at the end of the problem. So, now that we know what C is, let's go back to that purple equation that I had a moment ago, and let's substitute that C value in there. So the natural log of the absolute value of, and now we're back to just y's and x's, absolute value of y minus 1 equals negative 1 over x, and with a plus C at the end, that is now a plus 1/2. And once again, everybody, our goal is to take this equation here and solve it for y strictly in terms of x. And this gets interesting. So let's get working on this. The first thing we need to do, guys, or I should say the last thing happening on the left side of this equation is the natural log. And how do we undo a natural log? We exponentiate it. So we do e to the left, and now this is goofy, e to the entire right side as a power. So on the left, the e and the natural log cancel, but the absolute value is still there. Absolute value of y minus 1 is equal to, now what we have here is e to a some power. So I could write that if I wanted as e. I think this would be cleaner if I switch the order, make it a power of 1/2 minus 1 over x. But the other thing I want to show you that you very often see here is a property going way back. Let me remind you guys of something from Algebra 1. X squared multiplied by x cubed equals x to the 5th. I hope everybody feels comfortable with that. What that tells us is when you are multiplying two monomials together, you add their exponents. Now, another way I could have written that is instead of x to the 5th, I could have written it as x to the 2 plus 3 power. And if I read this property backwards, I could say that a monomial to a some power can be broken up into the product of those two individual monomials. So with that in mind, you will occasionally see this written this way, e to the 1/2 multiplied by e to the negative 1 over x power. A tricky thing about solving diffie-qs and initial value problems, guys, is that there's often a lot of different ways to express the same solution. So I've got it two different ways on the right here. Both of them are fine. And I'm not going to sit here and tell you guys it's got to be one way or the other, but I will tell you that the majority of times I think you're going to see it written this way, so I'm going to run that route from here. Now, back to our overall goal. Our overall goal is to get y by itself. So what's happening to y right now? Well, the first thing happening to y is the minus 1. The last thing happening is the absolute value. And I don't know that this has come up all that much for you guys over the years. To get rid of an absolute value, you're going to put a plus or minus on the other side so that absolute value of y minus 1, I'm going to leave off the absolute value and now just write this as plus or minus e to the 1/2 multiplied by e to the negative 1 over x. Last thing we need to do now to get y by itself is add 1. So we're going to get y equals, and generally we like to put that constant, the 1, in front of the plus or minus here. E to the 1/2 multiplied by e to the negative 1 over x. Now, everybody, we are not quite done yet. We got one thing left to do. We did isolate y and get it expressed simply in terms of x. But one thing I need you guys to hear loud and clear. An initial value problem's solution will never contain a plus or minus in it. Now, if that seems inconsistent to you guys with something I said a while ago, 2 slides ago, where'd it go? 2 slides ago, here we go, we did have a plus or minus in the answer. But this was not an initial value problem. They didn't tell us a specific point that this function passed through. So if there's a plus C in the answer, there might be a plus or minus. However, here, there aren't 2 different solutions to this equation. There's only one, and only one of those 2 cases, the plus or the minus, works with this initial condition with the point 2, 0. So our last job is to figure out here, guys, that if we want this last equation here to contain the point 2, 0, it is one or the other here, plus or minus, but not both. So let's see if we can't figure that out and see if we can't do it mentally. All right, guys, what I know is that when x is 2, y has to end up being 0. So actually, as I'm looking at it right now, I kind of wish I had stuck with this version here rather than this one. If x is 2, let's think about that. This power right here becomes 1/2, so that's 1/2 minus 1/2. The exponent becomes 0. So all of this is e to the 0 power, which is 1. And the question now becomes, is it 1 plus 1, or is it 1 minus 1 that's going to get us a y value of 0? The answer to that is minus. So this is going to be 1 minus, and again, I wrote it this way, so I guess let's do it again. E to the 1/2 power multiplied now by e to the negative 1 over x. And this right here, you guys, is the one and only solution to this initial value problem. So again, I'm going to reiterate, you will never leave a plus or minus sign in the final answer to an initial value problem. If you were able to solve for C, only one of those works to get you the initial condition, in this case of 2, 0. So we need to make sure that we figure out which one of those it is. We can't leave it vague and uncertain in the final answer. All right, guys, that's everything we have there for 9.1. Hopefully not too bad of a section, so I think you guys will do okay on that homework. So let's dive into it and let me know when you have some questions.